So, welcome back. So, in the last class we have looked at type 2 alloys, and we have also introduced the special reaction called eutectic reaction, which happens when a liquid of a certain composition reaches the eutectic temperature, then the liquid transforms into two new solids, and such a reaction is called eutectic reaction. And then we also discussed why a eutectic reaction cannot be considered as a congruent solidification, it is incongruent in nature. Now, let us look at so of course, in type 2 alloys, what the way that type 2 alloys are classified are based on the solidification in the solid state, right. In the solid state they are completely insoluble, that means two materials A and B are completely insoluble in solid state, while they are completely soluble in liquid state. Now, let us relax the constraint on the solubility in the solid state, and instead of saying complete insolubility in solid state, let us say what happens if there is partial solubility in solid state, while complete solubility is there in the liquid state. So, that is why that is what we are calling as type 3 alloys, where the two materials are completely soluble in liquid state and partially soluble in solid state. That means, there is a solubility limit of A in B and B in A. Okay. All right. So, the phase diagram of such a system looks something like this. This phase diagram is a special case or the type 2 alloy is a special case of this phase diagram. For instance, if you look at this phase diagram and move this point F and point G, if you move point G towards right and point F towards left, then it looks exactly similar to our phase diagram of type 2 alloy, right. Otherwise, if you look at the liquidous line and this is our solidus line, and up to in this region it looks like your isomorphous alloys, where they will meet at some other point. So, this situation is somewhere in between the type 1 and type 2 alloys that we are seeing here. Okay. And this is an important alloy system to look at, because most metals are actually partly soluble in solid state, right. So, this is the most common type of phase diagrams, and you can clearly see here the Ta and Tb are the melting points of metals A and B, and Ta E Tb. So, that guy, that is our liquidous line TaeTb, and the solidus line is TaFGTb is our solidus line. And the typical examples of such a system which has complete solubility in liquid state and partial solubility in solid state are copper, silver, lead, tin and tin bismuth. All right. So, here we have single phase areas and two phase areas, right. So, here this is a single phase area, and again you have another single phase area here, another single phase area here, and here you have a two phase region, here two phase region, and this is also two phase region. So, totally you have 3 single phase regions and 3 two phase regions. And here please note that you do not have pure solids, you have solid solution alpha and solid solution beta. Okay. So, because there is a partial solubility of A and B in A, they do not solidify pure solids. Alloys of this type never solidify pure A or pure B, but a solid solution or a mixture of solid solution will be formed. So, the areas below the melting points of A and B are phase alpha, single phase alpha and single phase beta. Usually they are called terminal solid solutions, because they are towards the end. In between also sometimes you may have phase diagrams, between other compositions also you may have new phases, but the phases that form towards the end of very close to the pure solids are called terminal solid solutions. So, here alpha is a solid solution which is rich in A. So, that means the solid solution of B in A. So, that means A is my solvent and B is my solute in alpha. What is beta? Beta is the solid solution of A in B, that means B is my solvent and A is my solute, right. So, this is host and this is guest, whereas in alpha A is host and B is guest, okay. And in between you have alpha plus beta, this is a two phase region. So, you can easily see how the two phase regions are identified in this phase diagram, right. So, for instance, if you see this is a two phase region, what are the two phases? You draw a tie line, you see that it is hitting this line. So, right to that you have liquid phase and hence liquid phase is one of them, and here left to this boundary you have alpha and hence these are the two phases. Similar here, right to this boundary you have beta, left to that boundary you have alpha, liquid. So, liquid plus beta. Here in this region, left to this boundary you have alpha, right to that boundary you have beta, and hence it is alpha plus beta, okay. All right. So, the two phase areas are we have already discussed, liquid plus alpha, liquid plus beta and alpha plus beta, and at TE temperature you can see at this temperature there is a maximum solubility for this alpha, right. The solid solution alpha dissolves a maximum of 20% B. So, this is the maximum solubility, right, beyond that it cannot dissolve. So, alpha has a maximum solubility of 20% of B in A, that happens only at TE temperature. At any other temperature it will have a much lower solubility. For instance, at this temperature the solubility is only this much, at this temperature the solubility is only this much. So, the solubility changes, solubility limit changes as a function of temperature, as we have already seen in the sugar water syrup example that we have discussed in the very beginning of this module, right. Similarly, if you take beta at the same TE temperature, it has the maximum solubility of 10% of A, right, because it is 90, that means you have 10% A in B, which is described by point G, and the maximum solubility of B in A is described by point F. And with the further decrease in temperature, the maximum amount of solute that can dissolve decreases, right, because the solubility is decreasing with decrease in temperature in both the cases. All right. And here the lines FH and GJ. So, this is our FH line and this is our GJ line, and these two lines represent decrease in the solubility of the the solute atoms as you decrease the temperature, and these two lines are called Solvus lines. They indicate the maximum solubility of B in A and A in B as a function of temperature, and point E is again your eutectic temperature or eutectic point. All right. So, how does this microstructure look like is something that we will look at. So, we need to certain interesting aspects of these type of alloys. So, alloys of same base metals, but with different compositions. So, that means A and B are the same, but different compositions will result in different mechanical properties, and that is the reason why we need to study their microstructures, because the microstructure is going to be strongly influenced by the composition of the alloy and the cooling rate during the solidification. However, in this module we are not looking at cooling rate, we are assuming that the cooling is done and at a sufficiently small rate, which means the equilibrium cooling is done. So, effect of cooling rate will not be discussed in this module, it will be discussed at a later stage. So, the key to the properties of different alloys is the microstructure, and hence we will study the evolution of the microstructure for 4 different compositions or 4 alloys in 4 different regions of the phase diagram. So, this is alloy 1, alloy 2, alloy 3, alloy 4. We could also have another alloy in this region, but that will be similar to alloy 1 or alloy 4. So, that is why we are studying these 4 classifications. Now, let us look at alloy 1. Alloy 1 is 5B 95A, right. This is say 5% B and 95% A. So, the solidification of this metal starts, this alloy starts at temperature T1 and ends at temperature T4, right. And so, it enters the 2 phase region, then you will have liquid plus solid, that solid will be alpha solid solution, and when it comes down it again enters from the 2 phase region, all the solidification, all the liquid would have transformed to alpha, and then you will only have alpha. So, this alloy microstructure is very much similar to the case of isomorphous alloys that we have looked at, right, wherein the liquid starts solidifying at a temperature and then ends at another temperature, and when all the liquid would have transformed to another solid phase, single phase. right. So, this is very similar to our isomorphous alloy microstructure. So, you have a liquid and then up to T somewhere in between you will have solidification happening, and this is alpha and this is alpha grains, and by the time it reaches T4 entire solidification would have finished. As you are coming down, all that happens is the alloy composition is phi b, but everywhere you have the solubility at each and every temperature is much larger. So, it is actually not saturated, under saturated, and hence nothing will happen. So, the alpha will simply this as you are cooling down, it simply reduces the sensible heat. Basically the temperature of the solid reduces, nothing else happens as far as the microstructure change is concerned. Alright. So, it is very similar to our isomorphous alloy system. Let us look at alloy 2. Again alloy 2 is our eutectic alloy, right, because it is a eutectic composition. So, let us look at the microstructure. So, at alloy at this position you have everything is liquid, and now let us at T3 the solidification starts, and on the left hand side we are showing the cooling curve. So, here the solidification starts at this point, and then as you are cooling down the liquid starts becoming richer in B and alpha starts. So, the solidification solidifies, the liquid solidifies into not pure A, but into a solid solution of type alpha, that alpha, which means solid solution of B in A. So, alpha is a solid solution which is rich in A, right. So, it solidifies into alpha. So, alpha crystals will be formed and they grow over the time, right, and then the remaining liquid. So, by the time you are here you have some amount of liquid and remaining is proeutectic alpha. So, it is called primary alpha or proeutectic alpha. So, if you look at the composition, so like draw the tie line. So, here it is 20 B. So, that is the composition of proeutectic alpha, and the remaining liquid solution composition is equal to eutectic composition, that is here 30 B. So, the liquid is 70 B, so not 30 B, 70 B. That means that is our liquid eutectic composition in this particular system. Since the remaining liquid has reached the eutectic composition and the temperature is eutectic temperature, what should happen? The remaining liquid should go through a eutectic reaction, and when it goes through a eutectic reaction, that happens at constant temperature. That is why you see a constant line, because the remaining liquid up to here the liquid is crystallizing solid alpha, and then at this point the remaining liquid has reached the eutectic composition and eutectic temperature, and hence at constant temperature the solidification happens, and the solidification results in formation of two solids, a liquid transforming to two solids. Here the two solids will be two solid solutions, right. So, alternate layers of alpha and beta. So, the two phases will be alpha and beta, and it becomes a alternate layers of alpha and beta. So, let us say this is alpha and that is beta. So, this is alpha beta and so on, right. So, the final microstructure will be a proeutectic alpha which has been formed before the which has been crystallized from the liquid solution before the eutectic reaction took place, and the remaining liquid transforming to alternate layers of alpha and beta. Here we are forming alpha and beta because pure solid A and solid B cannot form because there is some partial solubility. And you can also calculate all the weight fractions based on the discussions that we had so far on different other systems. Okay. Now, let us look at alloy 3. Alloy 3 here again alloy 3 is also pretty straightforward. You have a complete liquid solution at temperature T3, small grains of alpha start solidifying, and you see somewhere in between you will have, you draw a tie line and you see that it is 50 B. So, the liquid composition will be 50 B and solid will be, that is alpha's composition will be 10 B, right. And if you further cool it down just above at this point on this line, then the liquid composition will be 70 B. So, that means eutectic composition, and solid will be 20 B, proeutectic alpha will be 20 B. So, whatever remaining liquid, whatever is the weight fraction, what is the weight fraction of this liquid? The weight fraction of the liquid will be this distance divided by the total distance. This distance is weight fraction of liquid here at this position is 20 divided by 50, because 20 minus 50 70 is 50, that is equal to 2 by 5, that is equal to 40%, right. So, the 40% liquid would transform to a eutectic mixture of alpha and beta. So, somewhere here if you look at the microstructure, you have proeutectic alpha which is 20B and eutectic mixture of alpha and beta. Okay. Now, let us look at alloy 4, which is an interesting alloy here. Now, let us first at this position everything is liquid, and at temperature T2 the liquid starts solidifying. So, that means initial alpha phase starts happening, and then at some intermediate temperature we are seeing the alpha solid solution, this is alpha, this is alpha, 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 and the remaining liquid. And here if you see the alpha, the composition of alpha is 5B and the remaining is liquid, liquid will be this is 40B, right. And now, the moment you reach temperature T5, all the liquid would have transformed to solid alpha, right, all the liquid would have transformed to alpha. So, that is like our isomorphous alloys. So, at this position you will have complete alpha, and here we have started with 15% B. So, all the alpha would have transformed to 15B, and if you further cool it down, right, what happens at N when you are further cooling it down, here the moment it reaches point N, the solidification, the solubility limit has reached saturated. So, that means at N it can have 15% B. So, we already have 15% B. So, that is saturated. The moment you come below, if you cool it down below this temperature point N, what happens? The solubility limit is only this much, but your composition has 15% B. So, let us say you are looking at H point H, your composition is having 15% B, but your solubility limit says that it can only have 10% B, alpha can only hold 10% B. That means, the alpha has become rich in B, richer than what it could hold, and hence what should happen? The additional B that is sitting in the solid solution should come out, because it is oversaturated now. But when this B comes out, the B cannot come out as pure solid B, because there is some partial solubility of B in A and A in B, and hence it comes out as solid solution beta, and this solid solution beta is actually dispersed everywhere throughout the alpha matrix. So, what will be the microstructure, what will be the weight fraction of that beta? That will be, so if you draw a straight line, tie line, it is in the two phase region, this line hits the GJ line at 95 B, and hence the composition of beta solid solution will be 95 B, and the weight fraction will be very small, only this much is the weight fraction of beta, and this beta is usually found, this beta solid solution comes out, the additional B that is sitting in alpha comes out as beta solid solution, and that is randomly distributed throughout the matrix and preferentially along the grain boundaries. So, these are our grain boundaries, right, these are our alpha grain boundaries. You may have beta sitting dispersed throughout the grain boundaries and also in the matrix. So, here because of the limited solubility, as you are cooling down, there is something more happening to the microstructure. So, still there is some events taking place because of the limited solubility, and hence the position of the solvus line is also an important aspect to be paid attention to, right. And please note that in this particular system, you are after T5 you are entering a single phase region. Since you are in a single phase region, you do not have a tie line concept, and it does not, although you are crossing through the temperature TE, there is no liquid anymore, everything is solid first of all, and there is no reaction taking place. So, that means you do not see eutectic mixture in this particular microstructure. So, although there is there are several alloys which will form eutectic mixture, but this particular composition is not going to give you any eutectic mixture. That in that sense alloy 4's microstructure is very different from alloy 2 and alloy 3, right, as also from alloy 1. Alloy 1 is like very simple microstructure like isomorphous alloys, but alloy 4 is really interesting because it is going through. Please note that here it is again going from a single phase region to two phase region without actually going through any reaction, but just by giving out B from the excess B. So, because of the oversaturation of alpha solid solution with B, the additional B has to come out, and that comes out as beta solid solution, and that will be dispersed uniformly within the matrix. So, you are actually going from a liquid solution single phase region into a two phase region liquid plus alpha into another single phase region alpha, and again entering a two phase region alpha plus beta. Okay. So, that is about alloy 4, right. So, the microstructure looks something like this, and we can also in the two phase region we can calculate what is the weight fraction of beta. So, we can see that if you are drawing this line, this the weight fraction of beta will be Hp divided by Hj, Hp will be 5 divided by Hj is about 85, that will be about 5.88% when you are looking at the alloy 4. And if, please note that if the beta phase happens to be a relatively brittle phase, let us say that the beta element A and B are there, let us say A is a soft version and B is a brittle phase, and if the beta phase is relatively brittle, then what happens is because of the distribution of this beta phase throughout the microstructure, this beta brittle phase can actually make the material vulnerable for failure, because it may not, because of its brittleness it may not be very strong or ductile. And so, from this particular alloy composition we can understand that the microstructure plays a critical role in understanding the strength of an alloy. So, the strength of an alloy, as we have discussed, that is determined by constituents of the alloy, particularly if the phase is continuous throughout the alloy, and that is what happens particularly for alloy 4, because the beta phase will be continuous throughout, because the alpha everywhere has additional beta and the additional B, and that B comes out as beta, and then it gets segregated there as beta phase, and it is continuously distributed throughout the alloy. All right. So, a real system that has such a alloy phase diagram that we have discussed so far, type 3 type of phase diagram is lead tin system, which is very well known to us as a solder, which is used for solder joints, right. So, here alpha lead is on the left hand side, tin is on the right hand side, lead is soft and tin is known to be relatively harder compared to lead, and you have alpha solid solution, and this is our beta solid solution, and this is our solvus line, these two are solvus lines, and this is liquidus line, and this is solidus line, and that is our eutectic point, right. So, eutectic temperature is 183 degrees Celsius and eutectic composition is 61.9% tin. All right. So, now again if you look at the microstructures, it is like a alloy 1 that we have discussed. So, you have liquid, and then that will be forming in this two phase region, you will have alpha and liquid, and by the time it comes here you will have complete alpha, right, and the weight fraction will be, the composition will be C1, and it is a single phase region. It is exactly like our isomorphous system that we have looked at. And now this is the alloy 4 type that we have just now discussed, right. So, you have complete liquid, and then you are entering two phase region liquid plus solid, again you are entering pure solid, not pure solid, a single phase alpha, all are alpha grains, and by the time you cross this line you have oversaturated, the oversaturated alpha will have to give out B, but it cannot give B as pure B, but it gives out as beta, and hence this beta phase is continuously distributed throughout the matrix, and if this beta phase happens to be a brittle phase, that can be detrimental for applications in which we are using this component. And depending upon the nature of this beta, that the mechanical properties can be significantly engineered. And if you look at the eutectic composition, eutectic alloy, and again you have liquid, and at this point position you will have formation of alternate layers of alpha and beta. So, here the blue one is, let us say blue one is beta and the pink one is alpha. So, you have formation of alternate layers of alpha and beta. If you look the such a system under microscope, you will see these alternate layers of alpha and beta, and this is one grain and this is another grain 1, grain 2, grain 3, grain 4, all of them having these alternate layers of alpha and beta, right. So, why these alternate layers of alpha and beta forms? So, as we have discussed, let us say a liquid here is actually having certain composition, and then that is solidifying alpha, the surrounding liquid becomes richer in beta or richer in B, and instead of forming this B elsewhere, it is much easier for B to travel to the neighboring grains. That means, the solid state, the atomic diffusion, if you are forming alternate layers, the diffusion, atomic diffusion need to take place only over a shorter distance rather than forming individual grains farther away from each other, right. So, the reason why the reason for this alternating lamellar structure is because the atomic diffusion of lead and tin only need to occur over small distances if we are forming alternate layers. And what happens, this is like our alloy type 2 that we have discussed so far, and you will have proeutectoid alpha, this is proeutectoid alpha, and then at this position the remaining liquid, the yellow portion, will form alternate layers of beta and alpha. This is our beta and that is our alpha, right. So, if you look at the microscope, you see this proeutectoid alpha and eutectic mixture of alpha and beta, and obviously you can calculate all the weight fractions by drawing the tie line and using the lever rule. Alright, so what are the properties of these eutectic alloy systems? So, the properties of multiphase alloys in general depend on the individual characteristics of the phase, right. What is the individual characteristics of each of these phases, and the distribution of the phases in the microstructure, whether they are continuously distributed or not. If they are continuously distributed, what is the characteristic of the continuously distributed phase, and so on, and what is the amount of that phase and the number of phases that are present. So, these are going to determine the mechanical properties or in general the properties of the alloy system. So, for several commercially important eutectic systems, one phase is known to be relatively weak and plastic, and other phase is hard and brittle. So, one is soft and ductile, another one is hard and brittle. A typical example for that is aluminum silicon system, and when we are dealing with these things, eutectic systems, the strength of this these alloys increases towards the eutectic composition. So, the strength of the alloy from pure A to pure A and pure B, when you are reaching the eutectic composition from both sides, at the eutectic composition you usually have higher strength. So, the strength of the alloy increases towards eutectic composition as approached from plastic side, not from the as we are approaching from the plastic side, not necessarily from the brittle side. And beyond the eutectic composition, the strength decreases due to increase in size and amount of proeutectic brittle phase. Because the brittle phase is increasing, the you will have reduction in the strength, and these systems show, that means the eutectic system show a maximum strength at eutectic composition, because after the eutectic composition, if you have a brittle phase, that is going to be detrimental for fracture. And how do we go about improving the mechanical properties if you have these continuous phases distributed throughout the system, and then they are going to be detrimental to the mechanical behavior. So, how do we go about improving the mechanical properties? So, there are typically two methods. We can use cold working, or that means you apply deformation to the material at room temperature, it is called what is called cold working, or heat treatment. Heat treatment is one of the most popular ways to enhance the mechanical properties after the solidification of a particular component of an alloy. And for most important heat treatment process for non-ferrous metals is edge hardening, is a special kind of heat treatment. So, the details about edge hardening can be read from the textbook of Sidney H. Avner, or from the textbook of Callister's textbook on material science and engineering. And so, this age hardening primarily requires partial solid solubility, which is the case for type 3 alloys, and it needs to also have, it will have greater solubility at higher temperatures, which we know that, and then these two conditions are true for type 3 alloys, right. They have a higher solubility at higher temperature and they have partial solubility, and using these because they possess these two properties, age hardening can be used in order to enhance the mechanical properties, right. This is one of the heat treatment processes. We will look at different other important heat treatment processes in the module that we are going to discuss after this phase diagrams. If you want to understand more about the age hardening, I encourage you to go through the textbook of Sidney H. Avener's Physical Metallurgy, or you can also refer to the other textbooks that are mentioned at the end of this in the references of this module. All right. So, with that we will stop here and we will look at type 4 alloys and type 4, 5 and 6 alloys in the next class. Thank you very much.